It will make your node much more scalable, and it's also the recommended way to write node in ROS2 directly from the ROS development team. So first, we will create a class. Let's call it myNode. So the class should of course be named after what you want to do. If this is a camera driver, then you will call this camera driver node, okay? And we will make this class inherit from node, from the node object. So that is the way to create a node. You create a class inheriting from node object. Then we will write the constructor of the class. And we will directly call the super function init. So that we call the init function from the node, and we will give here the name of the node. And then we can also use this line. So instead of node get logger, we will actually use self, because self for this object, which is a node, so we can directly call the logger from self. And here we will remove that. Instead of creating a node object, we will create a myNode object. And well, that's it. This node is exactly the same as before, but using object-oriented programming. Let's run the node. So we will compile again. Let's find the Colcon build line. Okay, and if we run node, everything is the same because we didn't change anything. And that will be your template for writing ROS2 Python node. I will give you the template later on this section, so you can directly kind of copy and paste that every time you want to create a new node. You will need to change, of course, the node name here and the node name here. And if you want, you can put a log on it. And now let's actually, because this node still does nothing apart from printing a log, let's use one of the most basic and common functionality in ROS, which is a timer. A timer will allow you to call a function with a given rate. For example, you want to call a function at 10 Hz, then you use a timer. So let's do that. We will do that directly inside the class that we've created here. And before we create the timer, we need a callback function. So let's call it timer callback. Okay, and in this function, we will self get logger info, and let's say hello again. Okay, so we have a function that says hello, and then in the init function, we will do self create timer. So this is a function from the node object that we can directly get with self. The first argument is the period between two callbacks. So let's say we want to print at 2 Hz. So 2 Hz is 0.5 seconds, so one time every 0.5 seconds. And then we need to give a function to call, and we will give the function timer callback, self timer callback, because the function is defined inside the node. And now let's run this. So again, we can build it. So it will be installed, and we can run it here. Okay, we have hello printed every 0.5 seconds. Great. You can press Ctrl+C to kill the node. And let's improve a little bit our node. We can, for example, add a counter, self counter 0. And let's say that we increase the counter by 1 every time the callback is called. And we will simply print hello plus the counter value. Okay, so what this code will do is initialize a variable here to 0. Then we print a log. We create a timer with a 0.5 second between each callback. And then we give a callback function, which is this function. And in that function, we increase the counter every time, and we print hello counter. Okay, so everything here will be executed when you write this line here, when you call the myNode constructor. Okay, and then the RCLPy spin will make the node spin. So the timer will continue to run while the spin is still running. The timer will run, and you will see that line printed until you press Ctrl+C, and when you press Ctrl+C, the spin will exit. And your node won't be spinning anymore, and thus will not be able to do any kind of callback, like a timer, subscriber, everything else. So let's run this again. And as you can see, if you have an error, a syntax error in your Python file, then you will get the error when you build the package and when you try to install the executable. So it will not only create an executable, it will also check that the syntax is correct. So now that the syntax is correct, it should work. Okay, and we can now execute the node and hello 1, 2, 3, etc. So as you can see, we can easily create a complete functionality with just a few lines of code. And now that you can write your code inside your custom node class, this main function here will always be the same. You initialize ROS2 communication, you create your node, you make your node spin, and when you press Ctrl+C, this exits, and you shut down ROS2 communications. In this lecture, you will learn how to create a C++ node. You will write the node, compile it, and run it. We will follow the same order as we did for the Python node. So you will go in the source folder of your workspace, and here we will go in the C++ package. In the C++ package, we will also go in the source folder, which is now empty, and we will create our first file here, for example, my first node.cpp. And now we can edit this file right here. So let's write a main function. And to be able to use the ROS2 functionalities with C++, we will actually include RCLCpp. So let's do that. Include, you can find it under rclcpp/rclcpp.hpp. Okay, and let's save the file. And as you can see, we get a warning from VS Code. So this is only specific to VS Code, right? This will work if we compile it with Colcon build, but with VS Code doesn't know the path here. So we will need to add it manually. So to do that, you press Ctrl, Shift, and P. Okay, and you can actually type C and C++ configuration, and you will find that line, edit configuration, JSON. And this will create a .VS Code folder in the source directory here, because we use that as the base folder for VS Code. And you will be able to edit the C and CPP properties. So what we'll do here, we will include another path. And which path is that? It's simply the include folder of your global ROS2 installation. So you can find it under /opt ROS, and then Foxy, and include. If you see what's inside include, well, you have all the packages that you installed during the installation. You can see it's quite a lot. And that is all of the H and HTTP files you can use in your code. If you install more packages, then more HTTP files will be available here. So what we do is simply we take this path here, and we can add it right here, save the file, and that should be it. And yes, it's working. Now, if you do that, CPP, okay, you have the auto-completion, which is working. So the first thing we do, again, is to initialize ROS2 communication with RCL CPP init. And we need to pass the argc and argv from the main function. So we initialize ROS2 communication, and guess what? At the end, we will shut down, just like in Python. And now we will be able to create a node between those two lines, and let's use the auto type node, and we will use std make shared. The type is RCL-CPP node, so you can directly find the node object from the RCL-CPP. Okay, and as a parameter, we need to give the name of the node. So let's call it CPP test, just as we did for Python. PyTest here is CPP test. So as you can see, we use std make shared to create a shared pointer. So auto will be a shared pointer which has a node. If you are familiar with std shared pointer, maybe you should check a little bit more on your own. The documentation for shared pointer is quite complete, and you have many examples on the internet. Because for C++, ROS2 uses shared pointers everywhere. So basically, it's great because you don't need to use new and delete manually. When this shared pointer will go out of scope, then it will automatically destroy the node which is inside, and everything inside the node will be destroyed. And you don't need to manually check if the pointer goes out of scope, etc., etc. And now let's make our node say something. So here we will not directly use a getLogger function like in Python from the node. We will use RCL-CPP info like that, and node getLogger. So we use the getLogger inside the RCL-CPP info function, and we can say hello here, hello CPP node. Okay, and let's also make the node spin, RCL-CPP spin, and we pass the node. So the spin function expects to receive a shared pointer to a RCL-CPP node, which is correct in this case. Alright, so that is a very minimal C++ node. When the main gets executed, first it will initialize ROS2 communications, then you create the node, so it's a shared pointer to a node, you give it a name. Note that the node is created inside the executable, it's not the executable, okay? And then you make it print something and you spin. So when you spin, like in Python, when you spin, it will pause the program here, and it will keep the node alive, and every functionality you implemented for this node. For now, we don't have any functionality, so nothing will be done. And finally, after you press Ctrl+C, the spin will stop. So the node will stop spinning, and the shutdown will be called. So all of the ROS2 communications will be shut down. And then the program exits, and simply the node will be destroyed, because with shared pointer, you don't need to worry about that manually. So now let's run this code. So of course, we can't directly run the C++ file like that from the terminal. We will need to compile it anyway. So we will compile it, and then we will install it. To do that, we will use the cmakelist.txt. Actually, I will clean some of the lines. Here, we don't really need the default to C99. We'll only use the default to C++14, and I will remove the tests, okay, just to make this course a little bit clearer with the minimal code. So we have dependency to RCL-CPP, it's already here. And now we will use add executable, and we need to give a name to the executable. Let's call it C++ node. So that is the executable. That is not the name of the file, and that is not the name of the node, which is different. Okay, those are three different things. And this is from the source folder and the my first node.cpp file. So the source folder here and this file here. We will also need to link the dependencies with payment target dependencies. So this is not a standard CMake declaration, right? It's specific to payment, which is the build system. So CPP node, which is the executable, and then we will link the RCL-CPP library here. So those two lines will actually create an executable, but the executable will not be installed yet. So if you just compile that, you won't be able to run your node. So that's why we will use install with targets. Okay, we will put the CPP node here, and the destination will be under lib with the project name. Okay, so that is the lib folder, which will be inside the install folder of the ROS2 workspace. Okay, that is similar to what we had with the Python package in here. Okay, you have the lib folder here. So we will choose to put the executable in that folder, followed by the project name, which is simply the name of the package. So here we create an executable, and here we install it inside the workspace. Now we can go back to the workspace and Colcon build, and let's use packages select. So we don't build everything, my C++ package. Okay, and if we go to the install folder, my C++ package, inside we have a lib folder, Okay, and the name of our package, which is exactly what we asked for. And here what we get is an executable, which is cpp node, and that is what we asked here. We asked to create an executable and then to place this executable into the lib folder here. So we can run this executable, and it's working. We have hello cpp node, and the node is spinning, so we can kill it with Ctrl+C. And now, of course, you will not always have to go to the install folder and go to this path and manually start all the node. It's installed, so you can use the ROS2 command line tools. Let's, in a new terminal, let's source the bash rc, so it will source the ROS2 workspace, because you've created a new executable, so it's always better when you create something new to source the workspace. And let's use ROS2 run my cpp. You can press tab, okay? If you press tab, not enter, press tab 2 times, you have the auto completion. If I press tab 2 times, I get all the nodes that I can start. I mean, all the executables, of course. And cpp node, okay, it's working. So with just this command line, we can start our node. And that is a minimal C++ node. And now we will see how to improve this node with object-oriented programming to make it more scalable, and so we will add a few functionalities to it. Node class, and the timer will allow you to call a function at a given rate. So first we will create a timer callback, and we will make it private here. So timer callback, and what we do inside this is simply get logger. We will just print hello for now. Okay, and from the constructor we will create the timer. So to create the timer, we first need to declare it. We will declare it here as a private member of the class. You can use rcl-cpp timer base and then shared pointer. So this is specific to ROS2. It's kind of a helper. Okay, you can use shared pointer instead of using std shared pointer of the timer base class. Okay, so for many of the rcl-cpp functionalities, you will have shared pointer, shared ptr at the end. So that is the timer, and it's actually a shared pointer to the timer. Okay, and now we can initialize this timer, saying this create. Now it will be wall timer, okay, not create timer. And again, we need to give 2 arguments. The first one is a duration, and for that we will use std chrono, and let's say seconds with an integer with 1, so just 1 second. And the second parameter is the timer callback function. So because this is in a class, we can't just use the timer callback like that. We will need to use std bind to bind this to the wall timer function. And in std bind, you will write my node like that, timer callback, so you can find the function here. Okay, so reference to the name of the function, and then you will add this. So this is this node, this class. So the function will be bind to this. Okay, it's better like that. So you can press Ctrl+Shift and I in VS Code to put some order in your code. So the syntax in C++ is always a little bit more complicated than in Python, but for example, for std bind, you just need to learn that you should use it like that, and it will always be the same. When you create a wall timer, you will use an std chrono with duration, and then std bind with the method you want to call, and this to reference this object. So now we can compile again and execute it again. And as you can see, we have hello every second. I press Ctrl+C and it stops. So when I press Ctrl+C, the spin will end, and there's all the callbacks. So for example, here we have 1 callback, and the wall timer will not be able to call this function anymore, and then of course the node will be destroyed. Let's add a counter to make it a little bit more interesting. So we will add a counter here as an attribute, and initialize it here. Counter at 0, okay. Here we will do counter ++, and we can add a counter to our log like this. So it's a little bit like a printf function. You will put your string here, and then you can put the different variables you want to use in your string. So the counter is first declared, then we initialize it when we create the node, and then the wall timer will call the timer callback every 1 second here, and every time the counter will be increased by 1, and we print hello counter. Let's do it again. So let's see, if I simply start it again, you can see that we don't have the new version, so you need to actually build it, so it will compile it and install it. And let's run it, and hello 1, hello 2, etc. It's working. So congratulations, you have now written a complete ROS2 node in both Python and C++. In the next lecture, I will give you a template that you can use for any of your ROS2 Python and C++ nodes. And that template will also be the template that we will use, that I will personally use for the rest of this course. Because as you can guess, writing all the boilerplate code is quite annoying, especially if you can gain 2 or 3 minutes every time. In this lecture, you will learn a little bit more about the ROS2 architecture to understand the different client libraries you can use for different languages. So for now, in Python you have used RCLPy, and in C++ you have used RCLCpp. You might wonder, where do those libraries come from, and why do they both start with RCL? Well, RCL is a ROS2 library, and it means ROS Client Library. RCL is a pure C library, which contains all the core functionalities. Under RCL, you have the ROS2 middleware with DDS. DDS means Data Distribution Service. This will handle all the communications in your application. I won't give more details about that for now. All you need to know is that RCL is basically the lowest ROS2 client library you can use, and it is the bridge with the ROS2 middleware. The RCL is the base library for ROS2, but you won't use it directly. Instead, you will use other client libraries that are built on top of RCL. For example, RCLCpp, which you've just seen before in this section. RCLCpp is a C++ client library, which basically provides a binding with RCL functionalities. In your code, you simply use RCLCpp. And the same is valid for Python. The RCLPy client library is built on top of RCL, and then you use RCLPy in your Python code. It means that whether you program with C++ or Python, well, the base library is the same. So C++ and Python are the two most supported languages. But as you probably guessed it, we can add any other language on top of the RCL library. In fact, some of them already exist. For example, RCL Node.js for Node.js, RCL Java for Java, etc. Well, all of that is a simplified view, but this should help you understand why we are using RCLCpp for C++ and RCLPy for Python. Now you can create your own Python and C++ nodes. You've also learned how to launch them. For Python, you can, for example, directly execute the script, and for both Python and C++, after you install the node, you get an executable inside the install folder of your ROS2 workspace. And finally, you've also seen that you can use a command line tool named ROS2 run. No need to navigate to a specific folder anymore, and as you'll see in this lecture, it will give you more control over the node you are starting. So let's experiment with the ROS2 command line tool. You will see the ROS2 run that you already use, and some other tools that you will use in the future. So when you open a terminal, the bash RC will be executed, and as you can see at the end, we have the line to source our ROS2 global installation and the line to source our ROS2 workspace. So make sure you have those two lines inside your bash RC. And at any time, you can also source directly bash RC if you are not sure that the new version, the addition you made were sourced. So let's use the ROS2 command line tool. If you press tab twice, you will see all the commands that you get. There are quite a few, and you've already seen ROS2 run here and ROS2 package to create a package. And we'll see some other ones in this course. So if you press ROS2 run, and this command expects you to give a package and an executable. Okay, so we can launch any executable from the ROS2 global installation folder and from the ROS2 workspace. So if you want to launch, for example, a package from the demo nodes C++, and let's say the Colcon that we launched before, this package was installed globally, and this is an executable from this package. So you just press enter, and it will start the node. And if you press tab twice here, okay, tab, not enter, pay attention to that, you will see all the executables for this package. So as you can see here, this demo package has quite a few executables. And of course, we can start our own node, so from my Python package, for example, and if you press tab twice, you have the list of executables, and as you can see here, we only have one executable for now, so you can just type P and press tab and get the auto-completion. Okay, and it works. What you can do is type ROS2 run -h for help, and you will get a help message for the command, and for every command, you will be able to use that to get some help and some documentation. So as you can see here, we need positional arguments, the package name, and the executable name. So now let's open a few more terminals. Okay, like that. I will put screen in 4. And here, so every terminal here is a new session, and the bash RC was sourced, so the ROS2 global installation and the ROS2 workspace were sourced. So let's start our node again. So ROS2 run my Python package Python node, which is the executable, and the executable will start the node by test, we can use the command line ROS2 node, okay, and if you press tab twice here, you have a second action. So ROS2 node, and then, for example, list, which will list all the nodes in the environment. And as you can see here, we have one node, which is by test here. If I kill the node, I start ROS2 node list again, and of course, nothing is printed here. So ROS2 node list will allow you to see all the nodes running in your environment. Let's start the node again. We can see ROS2 node list will print by test. You can also use ROS2 node info, okay, this here, with the name of the node. And this will give you some information about subscribers, publishers, etc. So as you can see, we already have 2 publishers, and we have 1, 2, 3. We have 6 service servers. The publishers and service servers you see here will be here for all your nodes. And here you can see, for example, we have ROS out, the publisher to ROS out. We'll see later what is the publisher. But when you print a log here, when you send a log, this will go to ROS out also. And ROS out will get all the logs for your application. And then you have some publishers and service servers for the parameters. And so each node will handle its own parameters. We will see that also later. So if you want some more info, you can do ROS2 node-h. And you also get a help message for this command. So let's kill that here. And of course, if you try to get, for example, the information from a node that doesn't exist, you will get an error, unable to find node by test, because this node is not currently in the graph. We can see it with ROS2 node list. Okay, so now let's run this node again, and let's start ROS2 run my CPP package. Let's start the other node that we've created. Okay, we have 2 nodes in our environment now, and if you do ROS2 node list, you can see that the 2 nodes are present here. Okay, then you can do ROS2 node info with this one or with this one. So far now, you've seen the command ROS2 pkg create for a new package. You've seen ROS2 run with package name and executable name. And you see ROS2 node list to list all the nodes in your graph, and also ROS2 node info with the name of the node to get the information for this node. And it's very important to note that you should not have 2 nodes with the same name on your graph. And in the next lecture, we'll see how you can deal with that. And finally, I just want to show you what's happening if you don't source your environment correctly. Okay, so let's go to our bash rc, and let's comment this line here, and also this line here. So I open a new terminal. The bash rc will be executed, but those 2 lines are commented, so they will not be executed. If I do ROS2 node list, ROS2 command not found. So if you get that error, it means you have not sourced your global installation. So let's source our bash rc here, or you can simply open a new terminal. And now ROS2 node list will succeed. And of course, we don't have any nodes, so nothing's printed, but the command succeeded. Now I can do ROS2 run, for example, the demo node cpp will be found. I can launch the talker. Okay, but if I try to do ROS2 run my Python package with PyNode, then we will get package not found, because this package is not from the global installation, but from the local ROS2 workspace. So we need to source the workspace, and this should work. Okay, so you can see the kind of error you will get if you have not sourced correctly your environment. So I hope that can help you in case you get that error, so you know where does it come from. In your ROS2 application, you may want to launch the same node multiple times, but with a different configuration. For example, if you have a node for a temperature sensor, and if you have 5 temperature sensors, then you will want to launch the same node 5 times, and of course with a different name for each sensor. So one first important thing to know is that you can't launch the same node with the same name more than 1 time. Okay, so you won't get an error when you do that, but let's see what it does. So ROS2 run my Python package. We will launch our first Python node here. As you can see, ROS2 node list, we have the node here. We launch it again, ROS2 run my, so in a different terminal. Okay, and we don't get an error here, okay? It's working also. We have 2 nodes with the same name. And if we do that ROS2 node list, we have a warning. Be aware that some nodes in the graph share an exact name. And this can have unintended side effects. And as you can see, we have 2 nodes with the same name. And well, don't do that. If you do that, the nodes will be able to start, but then you will have many problems in your graph and in your communications, okay? If I do ROS2 node info by test, you also get a warning here. 2 nodes with the same name, and you are seeing the information about only one of them, okay? So previously in ROS1, it was impossible to do that, but in ROS2 now it's possible to start 2 nodes with the same name. I'm not sure why, but anyway, you should not do that, okay? It's important to know that. So how you can solve that problem with the temperature sensor, where you still want to launch that node multiple times? It's possible, and you can actually do that. You simply need to rename the node when you start it. So let's start the node again, and we will remap the name. ROS2 run my Python package PyNode. So you start like that, and then you will add arguments like that, ROS args. So every ROS2 argument you will add after this dash dash ROS dash args, and then you have dash r, or you can do remap like that. And we write double underscore node to point equal, and let's say ABC. And the node is now named ABC. If I do ROS2 node list, we have ABC, okay? If you check the code for the node here in my first node, you can see that we initialize the node with that name. But when you start the node with ROS2 run, you can pass some arguments to remap that name, and it will automatically change the name from there. Okay, so this actually is not a fixed value. It's not like it's hard code. Okay, you can always change it dynamically when you start the node with ROS2 run. So you can launch that node here, and you can launch the node again, ROS2 run my Python package, ROS args. Let's use -arg node, and let's say you can put any name you want. Okay, just follow the convention, and you start by a letter. Okay, you can then use letter numbers and things like underscores. Okay. So I start this node here, and I start this node here. And when I do ROS2 node list, we have two different nodes. So that is correct, okay? And let's start another one, ROS2 run my. So let's start the C++ one, ROS args, and let's name it. So of course, if I name it ABC, it's not correct because it will be the same as this one. So let's give it another name. And now we have 3 nodes running in our environment. So that feature will be quite handy when you want to duplicate some behavior. And you will see in the next sections of this course, you will also be able to remap almost anything from your node, topic, services, etc. So you will get completely different and unique nodes, all from the same executable. And that will allow you to configure your node at runtime without having to change any code every time you want to try a different configuration. In this lecture, I'm going to do a quick recap about Colcon, and please stay until the end because I will show you a new option you can use to work faster with your Python nodes. So to build your ROS2 workspace, you have seen that you can use Colcon build. Okay, so Colcon is the build tool for ROS2, which will use Ament as a build system. And when you do Colcon build, it will build all the packages that are inside the source folder. You can use Colcon build with packages select like that to build only one or multiple packages. So if I do my Python package, I will only build the Python package and not the other packages, okay? And you can get the auto-completion also with Colcon. If you don't have the auto-completion, make sure you have in your bash chassis, at the end of the bash chassis, make sure you have this line. And if you don't have that, then please watch the Colcon auto-completion lecture in the last section so you know how to do that. And finally, here's a tip that will help you work much faster with your Python files, okay? So for now, we have built our Python file of my first node, and that is the file we've built. So we have an executable we can run with ROS2 run my Python package, Python node, and okay, you can see here is the output of the node. Now, if we modify something in the node, let's say I add an exclamation mark here. So if I start the node again, the exclamation mark is not present. So we need to go here and to build our package. Okay, and once the package is built, we can launch it again, and we have the exclamation mark. So every time you modify your file, you will have to build it again, unless you use the symlink install argument. So you just use this flag like that after the Colcon build command. You can press enter. And this means that instead of launching, when you do ROS run, instead of launching the executable that was installed, it will simply create a symlink link to your file, which is directly here. So for debugging during the development time, this will be very useful. So if I run the node, I still have one exclamation mark here. And now let's add 2 other exclamation marks. Okay, I save the file, and if I run it again, I don't compile anything here, okay, I don't install anything, and we have 3 exclamation marks, okay? So as you can see, we don't need to compile the file again. First, you need to use symlink install, and then you can work with your Python file without having to compile again. So of course, you will need to compile once when you create the file, but after that, you can modify the file and work like that during development time. So it is only for Python, because in C++ you need to compile the file every time, so it will only be useful for Python. And also, if you want to do that, it's very important that if you go to your package, my Python package, so where the file is here, you have my first node.py. It's very important that this file is an executable, okay? If it's not an executable, the symlink link will not find the executable and you will get an error. So if you want to use the symlink install flag, make sure this is set as an executable. I will show you what is RQT and RQT graph. So RQT is a debug tool. It's a GUI tool that you can use to debug your graph, to debug your nodes, and many other things. And we will see more of RQT plugins along this course. So to start RQT, you simply type RQT. It is a node inside a package, so you could use ROS2 run, but instead we have a nice executable directly installed that we can use. So you have an empty screen, okay, because RQT is a collection of plugins. And the one we are interested about here is the node graph. Okay, so RQT graph, which will show you the actual graph. So we don't have anything for now because we didn't start any node. Let's start a node to see what we get here. So ROS2 run my Python package, my node. We have a Python node, and now we can refresh it. And you can see we have the node here. If I start ROS2 run my, let's start another node, my Python node, but we will remap to test. Okay, if I refresh, we have the Python test node and the simple test node. Okay, so as you can see, those nodes here, we choose that, those nodes are independent and they do not communicate between each other. So for every node you have in your graph, you can check with ROS2 node list. Here, you will find those nodes inside the RQT. And as you can see, we have a new node in our list because this window here, the RQT, is actually a node, so of course it appears in the list of nodes. If you remove the debug flag, you can see, and you take out the dead sync option, you can see that we have the ROS out topic, okay, and every node will publish to the ROS out topic. So every node is independent but still communicating with this topic. So when you put some log, it will go to the ROS out. And the ROS2 CLI daemon is something that is launched also when you start a node, so it will be easier for nodes to find each other. But for now, you don't need to worry about that. So basically, you can hide debug, and you have those two nodes. You can also directly start RQT graph with the RQT graph executable, okay, which is same but just faster. Okay, so RQT graph will be very useful when you want to know what's going on in your ROS2 graph. You will get a global overview and you will easily spot mistakes. We will often come back to RQT graph during this course. Let's experiment with an already existing package providing a simplified 2D simulation of a robot. This package is called Turtlesim. This will be a good opportunity to apply what you've learned with ROS2 tools in this section. And we'll often come back to Turtlesim during the course, and at the end of the course you will also have a complete mini project using Turtlesim. We will start the main Turtlesim node with ROS2 run Turtlesim from the Turtlesim package, and if you press tab and you don't have the Turtlesim package, it means that it's not installed yet. So to install it, you can simply type sudo apt install ROS dash. So the name of the distribution you use, if you use Foxy, it will be Foxy. If you use a different distribution, you will put a different name here, and Turtlesim. Okay, and now that Turtlesim is installed, we can open a new terminal to source the bash RC, or we can directly source bash RC here because the package was installed, but this terminal doesn't know it's here, so we need to source it before. And now ROS2 run Turtlesim. Okay, I press that twice, and we have the different nodes, and we will launch the Turtlesim node. And that will bring you a 2D window with a turtle in the middle. So you can see a node. For now, we've only seen node with only output in the terminal, but you can put anything you want in a node. It's just a program. You start ROS2 communication, you create a node, and then you can do anything. If you want to create some 2D visualization, 3D, if you want to do some networking, anything, and finally you shut down the communication. But you are free to do anything you want in this node. So we can see the node here. If I do ROS2 node list, you can see the Turtlesim node. So again, you can see the Turtlesim node. This is the name of the executable, and this is the name of the node, okay, which is different. Now we will, okay, let's change the layout like that. And we will start another node, ROS2 run Turtlesim, Turtleop key. And that is a new node, and you can use the arrows from your keyboard to move the turtle, okay, like that. So I simply move the arrows from my keyboard, and the turtles move in the screen. So this node actually, when it gets your input, it will send it to the Turtlesim node. And how to see that? So you have ROS2 node list, okay, you can see we have the turtle node. Now if I do RQT graph, with RQT graph and I refresh here, you can see we have Turtlesim node and Turtle, and they are communicating between each other. Let's use that, okay. So here, the Turtle will send a command velocity to the Turtlesim, and that is a topic. And if you want, you can also rename. So let's kill this and kill this. You can also rename. So let's use ROS args and remap the node to my turtle. So okay, and we can start this again. Okay, so it's working again. If I do RQT graph, we can see that we have the name, which is now my turtle. Okay, so you can rename also the node from Turtlesim.